which resulted in an adequate degree of modulation for the 2 GHz wideband CDMA ROF module. But apart from that, this results is a testament that if we improve the design, this radio free space optic system can be used for transmission of wideband CDMA signals. Another example of results I'll show is the transmission of wireless local area network service signals shown in this slide. The figures on the left, top and bottom, is the spectrum mass test for evaluating the quality of wireless local area network signal, and it's simply done by just using a pass-fail judgment of the spectrum mass test template. The top figure is the wireless LAN 802.11g spectrum mass test at 2.4 GHz, and in this case it's pass, and we consistently got pass from testing this 11G figure of merit every second, and we had no problems. But for the case of the wireless LAN 802.11a spectrum mass test at 5 GHz, this figure, unfortunately, it's failed. And also this, we noticed, we attributed it to the limitations of the ROF module we used in our experiment. Unlike the 11G ROF module, whereby we just did direct modulation of the laser diode, for the 802.11a 5 GHz ROF module required a high input voltage, so we used an external modulator. But unfortunately, the external modulator was still not providing sufficient power or voltage to the ROF module. That's why the spectrum mass test there is failed. We also did some throughput measurement by transmitting over a continuous period of time wireless LAN 11G signal and correlated it with the received optical power characteristics as shown here. So the left vertical axis is the throughput measured in megabits per second, the right vertical axis is the received optical power, and the horizontal axis is time. You can see that both the transmit and receive throughputs are well above 12 megabits per second, and only fall below this value at a period around midday, which is around 12 noon, which we usually consider a period of increased atmospheric turbulence, and atmospheric turbulence usually has a significant impact in the performance of free space optic systems. But all in all, these results also show if we design properly the ROF modules, the RRO FSO system can conveniently be used as for transmitting wireless local area network service signals. So due to limitation of time, I'll just give examples of those two wireless service signals transmission of our radio and free space optic system. To summarize, I presented a new innovative broadband wireless communication system based on radio and free space optic, which is suitable for application as a universal platform for providing convergence of fiber and free space optic communication networks. And the transmission performance evaluation of this proposed radio and free space optic system has demonstrated consistent performance in terms of specified figure of merit parameters for the various wireless service signals when we're transmitting them in the absence of severe weather conditions, for example, dense fog, heavy rain, or snow, and by using properly designed interface units. From the design concept, the performance characteristics and application areas, we have confirmed that this technology is well suited for deployment as an advanced wireless communication system in the emerging next generation network, and it has potential to play a key role in fostering digital inclusion. We don't expect to see this technology anytime soon, but we believe that for rapid maturity and adaptation of this technology, possibly early initiatives for standardizations in either ITU-T, ITU-R, or any other standardization bodies will be very beneficial. What we're working on now is to carry out further experiments with redesigned interface units, especially ROF modules, and doing these experiments in different weather conditions, and derive some data which will be helpful in the system design optimization and performance enhancement. We are very grateful for NICT for providing a grant to implement this project. I would also like to thank Osaka University, which were our project collaborating partners, for their very nice input, especially in ROF techniques. I would also like again to thank the ITUT, TSB for giving us an opportunity to present our work in this esteemed conference. And finally, but not least, I'd like to thank you, the audience, for being patient and listening to my presentation. Thank you very much.
Thank you, Kamwisha, for this interesting presentation. As far as I'm aware, at the moment there is no standardization activity in the ITU in the area of free space optics, but maybe that's a good idea to reconsider this. Floor is open for discussions, questions, comments. Yes, please.
Tsugino from NICT, but not in section funding you. And your research focused on performance analysis of radio signal transmission. And I would like to expect you further research on the performance of protocol layer or total throughput, because the total throughput, the distance of the data link layer the two points of communication processing the data link layer. The distance have a big impact on total throughput performance. I mean, so yes, radion fiber can extend the transmission distance in total. But on the other hand, future very, very high-speed wireless communication needs a short distance of the protocol layer processing point. So I think such a protocol layer performance analysis is necessary for your research. This is my comment. How do you think?
Thank you very much for the comment, and I absolutely agree with you about investigation in the protocol layer and throughput analysis, and I think this is what we're considering to do in the future for further improvement and optimization of our system. Thank you.
I think we have time for one more question. There is one. Yes, please.
I think your technology is dependent on the structure of the situation of the country, I think. For instance, Japan has lots of earthquakes, so all the buildings kind of characterize anti-earthquake structure. In that case, the building is so elastic, so even a very small wind can swing the huge building. So I think it's very difficult to track the a small spot, beam spot. What kind of technology you are using?
Thank you. It's a very good point, actually. I did not mention, but these systems are designed with automatic tracking and alignment mechanism, which makes sure that the transmitter and receiver are constantly aligned. So even if you have building motion, for example, the tracking mechanism in the antennas can keep the transmitters aligned to each other. And in this case, in this experiment we're doing, we have the antennas set up on the rooftop of two Waseda University buildings, which are about 10 floors each, as you can see here from something I got from Google Earth. And you do expect that during the day, usually you have heating effect and the building will expand, so the building will sort of be moving a bit. But because you have this automatic tracking mechanism, it keeps the transmitter and receiver aligned to each other. And we also have data where we collected in an event where we had an earthquake, as you just mentioned that there's a lot of earthquakes in Japan. And you can see that the interruption between the link was very minimal, like let's say in less than 1 minute, less than 30 seconds, the antenna was able to realign itself after this tremor. Thank you.
Okay, thank you for the interesting questions, for your responses. And, the next speaker would be